Okay, today we're going to talk about section 6.3 and 6.4, which involve solving equations involving logarithms or exponents. We're going to begin with exponents, but the process is extraordinarily similar between the two. The idea is that you need to isolate the special piece, in this case, the exponential. Once you've done that, you can cancel the exponent by using a log and then solve the new equation or inequality normally. We'll go through a couple examples of this before we look at logarithms. Let's start with this. 3 to the 7x is equal to 81 to the 4 minus 2x. So in this case, we will take a log base 3 of both sides. Why log base 3? Well, 3 is on the left as a base, and on the right, 81, we know is a power of 3. 81 is 3 to the 4th power. So a log base 3 will make solving here very straightforward. We can go ahead and we can bring the exponents out to the front in each case. So this will be 7x times log base 3 of 3 is equal to 4 minus 2x times log base 3 of 81. Then, using the properties of logs, on this side, log base 3 of 3 is simply equal to 1. So I'm left only with 7x. For log base 3 of 81, you may be able to see it straight away, but if not, log base 3 of 81, let's call w, which means that we are looking for 3 to the power of w is 81. 3 times 3 is 9, and I know 9 squared is 81. So that's 2 3's multiplied by 2 3's, or 3 to the 4th is 81. Thus, log base 3 of 81 is equal to 4. So we will have ourselves, this is still 4 minus 2x, multiplied again by 4. We've now got ourselves a regular equation that is pretty quick to solve. X is equal to 16 over 15. Let's go through a couple more examples here. This time, the issue is that I do not have an obvious base that I'm supposed to use here, because 7 and 3 aren't as closely related as 3 and 81 were. In this case, what you're going to do is you're going to just use any log that you want. Our numbers will have to be evaluated using our calculator, and that's okay. So let's just do an ln on both sides, because that's something that will be easier to plug in our calculator, and we will never need a change of base. So we'll take an ln of 7 to the 3 plus 7x is equal to ln of 3 to the 4 minus 2x. This means that I'll have 3 plus 7x multiplied by ln of 7, 4 minus 2x times ln of 3. Now we'll just have to go ahead and isolate x. Remember that ln of 7 and ln of 3 are simply numbers, so we can treat them as such. We'll first distribute, move all the x's to one side, and then divide to solve. So this will be 3 ln of 7 plus 7x, let's say 7 ln of 7x, is equal to 4 ln of 3 minus 2 ln of 3x. We'll move the x's on the left and the numbers on the right. So that will be 7 ln of 7x plus 2 ln of 3x is equal to 4 ln of 3 minus 3 ln of 7. Factoring out an x on the left-hand side, and leaving the right-hand side the same, gives us our final answer with division. 4 ln of 3 minus 3 ln of 7 divided by 7 ln of 7 plus 2 ln of 3. Now, we'll certainly need to use a calculator to get the answer here. So let's go ahead and switch us over momentarily to Wolfram Alpha. And I would plug in 4 ln of 3 minus 3 ln of 7 divided by 7 ln of 7 plus 2 ln of 3. This comes out to be, in decimal form, negative 0.09124, which is going to be our best approximation. Let's go through a couple more that we should be able to do without resorting to a calculator. Here, in order to solve this one, we'll need to get creative with our exponential properties, as there's no way for us to isolate the exponent without doing something new. We can't just put an exponent on each side because that 12 makes it more complicated. However, we will notice that 4 is equal to 2 squared. So I can rewrite this piece as 2 squared, and further as 2 to the x squared. If I say y is equal to 2 to the x, then we could rewrite this as y squared plus y is equal to 12, becoming a very straightforward quadratic. Y squared plus y minus 12 is equal to 0, giving us y squared, or let's factor here. So that'll be y plus 4y minus 3 will work, which means that y is equal to negative 4 or y is equal to 3. Switching back to exponential form, we need 2 to the x is equal to negative 4 or 2 to the x is equal to 3. Now, we can cross this first one off immediately. There is no power that I'm going to be able to put 2 to in order to get a negative number. I can't multiply by 2 by itself or divide 2 by itself to get a negative number. But 2 to the x equals 3 does have an answer. The answer will be log base 2 of 3 is equal to x, which we obtain by doing a log base 2 on both sides. Thus, x is equal to log base 2 of 3, which we can real quick punch into our calculator. Log base 2 of 3 is 1.585. Let's do one more example with exponents before we go on to logs. This time it's going to be an inequality. Now the idea is the same, we'll just have to remember that at some point we'll need to make a number line. But we'll start off just by solving the related equation. Taking a log base 2 on both sides. On the left-hand side, the log base 2 simply cancels out with the 2, and we're left only with what is on the inside, x cubed minus x. On the right-hand side, log base 2 of 1, well, log anything of 1 is always going to end up being 0, because it is asking ourselves 2 to what power is equal to 1, and 2 to the 0 is equal to 1. We can factor and solve this quite quickly. X squared minus 1, which gives us x plus 1, x minus 1, which means x is equal to negative 1, 0, or 1. We will put these numbers on our number line. Negative 1, 0, 1. And then, taking the related inequality to x cubed minus x minus 1 is less than 0, we'll plug into these things each time in order to determine what's going on. Now, the nice thing here is that because I have 2 to a power, I only really care about whether the power is going to be greater than or less than 1 in each case. So let's go ahead and take a look here. So we'll use our test values. Let's say we're going to use -1/2, -2, 1/2, and 2 here. So if I plug each of these in to the original, into just the exponent for the moment, we're going to make our table like always. -2, -1/2, 1/2, and 2. First, I'm just going to focus on the pieces in the exponent. We've got an x plus 1, an x minus 1, and then the entire exponent, which will be composed of this. So focusing just on this bit for now, if I'm plugging in -2, let's see, so this will end up being negative, 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 making the whole thing negative. The -1/2 will be negative here and here, but positive here, and 2 negatives makes a positive result. A +1/2 will be positive here and here, but negative here for a negative result. And 2 ends up being positive everywhere. Now, based on whether the exponent is positive or negative, that means that the final answer will also be positive or negative, because a positive exponent means that I will be larger than 1, and a negative exponent means that I will be smaller than 1. Remember, negative exponents create fractions. So the pieces that are negative are the pieces that will be our answer, because that will make this piece smaller than 1. The pieces that are positive will not be in our answer. We can put this on the number line. So we've got a negative here and here, a positive here and here. And we will obtain as our answer -infinity to -1 unioned with 0 to 1. Now let's take some time and look at logs. The idea is exactly the same, but we need to be very careful because unlike exponents, logs have a restricted domain. And a restricted domain often means that we will get an extraneous solution. Extraneous solution means that you do something during your solution process that looks like it should work and gives you an answer, but if you plug that answer back into the original, it won't work anymore. As an example, let's say I have something like x plus 2 squared over x plus 2 is equal to 4. Now, your first instinct might be, let's make this equal to 0 instead. Now, your first instinct might be to cancel the x plus 2 with the x plus 2, which gives you x plus 2 is equal to 0 and x is equal to -2. And that seems like it would work just fine. However, if we were to go back to the original and plug in -2, we would get -2 plus 2 squared over -2 plus 2, which is 0 over 0. And you're not allowed to divide by 0. So because we had division here, the process of solving ended up giving us an issue. With logs, we'll have to be similarly very careful. But other than this extra step at the end, it's exactly the same as exponents. Isolate instead of the exponent, we're going to isolate the log. We're then going to cancel the log using an exponent. We will then solve the new equation or inequality as normal, and we'll finally check for extraneous solutions being the new thing. Let's go through some examples. So we'll start off here. ln of x minus 8 squared is equal to ln of 2 minus x. The way that we cancel these logs with an exponent, we'll make both sides be the power of e. This is what I would write for the notation of that, but what I'm really doing is saying, okay, e to the ln of 8 minus x squared is equal to e to the power of ln of 2 minus x. These e's will cancel, and we are left with 8 minus x squared is equal to 2 minus x. We'll move everything over. X squared minus x minus 6 looks like it will work. So x minus 3, x plus 2, which means x should be 3 and negative 2. We'll plug these numbers back in and make sure we haven't done anything that's not allowed. If I were to take 3, 8 minus 3 squared would be ln of negative 1. And that's a big issue. On the other side, I would get ln of 2 minus 3 and also ln of negative 1. Now we see that this looks like it should be okay. ln of negative 1 equals ln of negative 1, but remember, you're not allowed to take an ln or any log of a negative number. So that's no good, and that's no good. We'll try the same thing out with negative 2. ln of 8 minus negative 2 squared comes out to be ln of 2 squared is 4, ln of 4. And ln of 2 minus negative 2 is ln of 4. This one is okay. There's no negatives inside our ln, so negative 2 will be an actual answer. Make sure you always take this time to check for extraneous solutions with log, because they will show up very, very frequently. Let's try another example here. This time, we'll have to once again use our properties in order to do some simplification before we can cancel. This time, because I have two different logs, I know I can combine them by using the addition algebraic property, giving us log base 3 of x minus 4 times x plus 4, all equal to 2. Then we will take both sides and make them a power of 3, which will give us x minus 4, x plus 4 is equal to 3 squared, which is, of course, 9. So x squared, that cancels, minus 16 is equal to 9. X squared is 25, and x is equal to negative 5, 5. Once again, we'll need to plug these back into the original. If I were to plug in negative 5, then I would get log of negative 5 minus 4 would be negative 9, which is a big no-no. So that's out, and that's out. But if I were to plug in positive 5, we would have log 3 of 5 minus 4. That looks okay. Plus log 3 of 5 plus 4 is equal to 2. That gives us log 3 of 1 plus log 3 of 9. Log anything of 1 is 0. Log 3 of 9, 3 to the power of 2 is 9. And that looks great. When you're doing your checks, the biggest thing we're concerning ourselves with is things that we're not allowed to do. Most notably, in this case, logs of negative numbers. This is the most important thing that you are looking out for, and make sure that this is what you are trying to avoid. Let's do an inequality now involving logs. Same idea as before. We'll first solve the associated equation, and then we'll make a number line. So first, 1 minus ln of x over x squared is equal to 0, which means 1 minus ln of x is equal to 0. ln of x is equal to 1. So in order to solve this, we can convert quickly to exponential form by taking an e on both sides. And we will get x is equal to e to the 1, which is equal to e. So e is our solution to the equation. Then we'll create our number line, and in addition to this solution, we'll also need to include the denominator being 0, which would be 0. So our number line will have 0 and e on it. We can plug in, let's say negative 1, 1, and 3, because e is about 2.7. It doesn't seem like any types of factoring will end up being extraordinarily helpful here, so we're just going to plug these in without anything weird going on. With -1, I see there's an immediate issue. ln cannot take a -1, so this area of our graph, I'm just going to X out. It's not positive or negative, it's undefined, so we won't even consider it. Thus, we only have two numbers to plug in, 1 and 3. So for 1, we will obtain 1 minus ln of 1 over x squared is what we are looking for. 1 squared, excuse me. Now, ln of 1, any log of 1 will be 0. This will be 1 over 1, which is equal to 1. When I go to plug in 3, I have 1 minus ln of 3 over 3 squared. Now, ln of 3, you're probably going to need your calculator for. So we have two options. Number one is simply use our calculator, but number two option is to choose a different number on our number line. 3 seemed like it would have been easy, but it ended up being harder to plug in. Whereas e squared, which is certainly larger than e, ends up being much easier. 1 minus ln of e squared divided by e squared squared. The reason this is simpler is because ln of e squared, I can use my property to bring this 2 down. 1 minus 2 ln of e over e to the 4th. 2 ln of e is simply 2, which gives me -1 over e to the 4th. Since e is a positive number, -1 over e to the 4th is negative. So this one is less than 0 for a negative here. This one was greater than 0 for a positive here. And of course, the left-hand portion of the graph is omitted due to the restriction on our domain for ln. Since we want less than 0, the answer we are looking for is e comma infinity. That's all we've got for today. See you next time.